Okay guys, so welcome back. Section 6.4, video 2, logarithmic functions. So on the last video we stopped on graphs. So I'm going to continue with graphs. And this is going to be the second case, decreasing graphs. Decreasing graphs. So I'm going to graph both exponential decreasing function and logarithmic decreasing function so we can see exactly that they are inverses. So let's start with exponential. Decreasing function. Let's review that. So y equal a to the power of x, and the exponential function is decreasing if the base is greater than 0, however it's less than 1. So we will graph y is equal 1/2 to the power of x. Okay, in this case base is 1/2. Okay, so again, to graph exponential function using 3 major points. So we have 1, 0. I'm sorry, not 1, 0, 0, 1, 0, 1. Then we have 1, base, and negative 1, 1 over base. So in our case, we have 0, 1, 1 and 1/2, and negative 1, 1 over 1/2, which will be negative 1, 2. So to graph the exponential function which is decreasing, let me plug in those 3 points. So we have 0, 1, y-intercept, 1 and 1/2 right here, and negative 1 and 2. So still the same shape, however, this function decrease. Okay, so this is y equal 1/2 to the power of x, decreasing function. Okay, don't forget that we have horizontal asymptote, y equals 0, horizontal asymptote. Okay, domain, still no change from negative infinity to infinity. Range, it's from 0 to infinity, that's the y values. Function, it's decreasing, and we have y-intercept. Y equal 1, that's the y-intercept, 0, 1. Okay, so now we're going to use that information and we're going to graph logarithmic decreasing function. So that's always going to happen when the base of logarithm is between 0 and 1. Okay, so we're going to graph y is equal log base a of x, and we're going to use example. We will graph y is equal log of base 1/2 of x. Okay, so to graph it, you graphing this logarithmic function with 3 major points. Please memorize them. Memorize 3 major points for exponential and just switch them for logarithmic function. So 0, 1 will become 1, 0. 1, a will become a, 1. And negative 1, 1 over a will become 1 over a, -1. So in our case, base is equal 1/2. So we're going to have 1 comma 0. We're going to have 1/2 comma a. And 1 over 1/2, it's 2 comma -1. So we use 3 major points from exponential function and we switch the coordinates. And we end up with 3 major points of logarithmic function. So let's graph this function. Okay, so I'm going to plug in the points. Okay, the scale is 1. So I have 1 comma 0, x-intercept, 1/2, comma 1. Sorry guys, that should be 1. 1/2 comma 1. So we have 1/2 comma 1. And then we have 2 comma -1. So 2 comma -1 right here. So this is our graph. Okay. This is y is equal log base 1/2 of x. Okay, like you see, this function is decreasing. And this function and the green function, I really don't want to graph them together on one number line because I didn't want to graphs overlap, but you should be able to see that they are actually inverses because they are symmetric with respect to the line y equal x. Okay, couple things. Okay, so let's just write down here. Domain, that's our x's. Again, like you guys see, are x's only greater than 0, which means from 0 to infinity. So inverses. Okay, range of exponential function was from 0 to infinity, so that range became the domain of the inverse. Okay, now range, which is our y values, no restrictions here, which is from -infinity to infinity, y values. Okay, so range of logarithmic function is the same as domain of exponential function. Okay, now look what happened. Our function is decreasing, so we know that already. We don't have y-intercepts, however, we have x-intercept. At x equal 1, we have a point 1 comma 0. Okay, exponential function has a y-intercept, and the most important, since domain is restricted, that means we're going to have vertical asymptote. Okay, x equals 0 is the vertical asymptote. Okay, so that's how you're graphing logarithmic functions. Again, I use the graph of exponential functions because we learned them in a previous section, and I just create the inverses. Okay, next what we're going to do, we're going to talk about finding the domain of logarithmic functions. So next example is about finding the domain of logarithmic function. So let me give you a note. To find the domain, like you see, for the domain of the basic graph, we have all the values which are positive, greater than 0. So to find the domain, of course of logarithmic function, I'm talking about logarithmic function, okay, solve the inequality. Okay, expression next to log has to be greater than 0. Okay, expression next to log greater than 0. Okay, and you guys going to see that. Okay, that comes straight from the graph. Okay, our x's are from 0 to positive infinity. And I'm going to use the problems from your textbook. This is number 41 from page 449. We need to find the domain, and they give us the logarithmic function f of x, which is equal log base 2 of x squared. So to find the domain, okay, without graphing, you always take the expression which is next to log. So in our case, it's x squared, and you solve the inequality. Has to be greater than 0. So how are you going to solve it? So here you guys have to think, okay, a little bit, because there's nothing to solve. So any expression bring to the second power, it's always positive, except, so think, this is always true, okay? Any number bring to a second power, it's always positive, except for x equals 0, because when x is equal 0, we have 0 to a second power, and that's equal 0. So we don't want to have x equals 0, okay, because our inequality is a strict inequality. So the domain is all real numbers. So all real numbers satisfy this inequality that x to a second power is positive, except x equals 0, okay? So all real numbers except x equals 0. It's our domain, okay? Because when x is equal to 0, you square that, you're getting 0. That's what we don't want it. Which, using the interval notation, you will write this down as negative infinity to 0 union 0 to positive infinity. So that will be the answer. And again, I really prefer interval notation. Okay, so let's do more. This is number 40 from the same page. You have to find the domain of function g of x equal ln of x minus 1. Okay, so I gave you the hint. To find the domain of logarithmic functions, you take the expression which is next to log, which is x minus 1, and you solve an inequality. That has to be positive. Solve for x. So we're adding 1 to both sides, and we're getting x is greater than 1. So that will be our domain. All the numbers greater than 1. Okay, that's our x values, all the numbers greater than 1. So using the interval notation, that will be from 1 to positive infinity. That's our answer. Okay, let's do a little more advanced. Number 46 from page 449. You have to find the domain. So again, we find domain in all those problems, and they give you function g of x, which is equal ln 1 over x minus 5. So to find the domain of logarithmic functions, this is what we always use. Expression next to log has to be greater than 0. So we solve inequality. So in our case, we have 1 over x minus 5. And that expression has to be positive. Okay, so how you're going to solve it? This is rational inequalities. I teach you how to solve rational inequalities. So what you're going to do, okay, since you have rational inequality, I believe section 5.4. Okay, what we know about rational inequality? Okay, so first of all, numerator is 1, so there's nothing to do. But here, you have to take that denominator can't be equal 0. So in our case, you're going to take x minus 5, and you're going to solve for x because that expression can't be equal 0. Solve for x, and you're getting x can't be 5. So now you're going to draw the number line, okay, because we're trying to find the intervals for which this rational inequality is positive. So we already know that our x values can be 5, okay? So that x not equal to 5, this one break down the number line into two intervals, from negative infinity to 5 and from 5 to positive infinity. So hope you guys remember what to do next. Next, we need to do the test. We have to check which interval is the solution of the inequality. Okay, 1 over x minus 5 greater than 0. So first I'm going to test the left side of the interval. I'm going to pick a number which belongs from to negative infinity, from negative infinity to 5. I'm going to pick the easiest case, so pick x equals 0. So when I pick x equals 0, I'm going back to my inequality, okay, and I replace x with 0, and I'm checking if that inequality is correct. So I'm having 1 over 0 minus 5, and I'm going to check if this is positive. So we end up with 1 divided by negative 5, and I'm checking if this is positive. This is definitely not true. So this interval, it's not the solution of the inequality. So next, what we're going to do, we're going to test the second interval from 5 to positive infinity. So test, let's do the test here. Pick any value bigger than 5. So I'm going to pick x equals 6, and I plug in that 6 into our inequality. So pick x equals 6. So we're having 1 over 6 minus 5, and we're checking if this is positive. Okay, so we're getting 1 over 1. It's definitely positive. Since this is true, this interval is the solution of inequality, which represents our domain. So yes. Okay, so the interval. So interval from 5 to positive infinity, it's the answer. Okay, so let's go back right here. Answer, that was an orange. So domain, it's from 5 to positive infinity. All the x's greater than 5 will satisfy our domain. And one more, and again, one more, I'm picking something what can give you headache with the homework, so hopefully that will help you. So let's solve one more with rational inequalities. Number 47, they also ask you to find the domain. So you have g of x equal logarithmic function with base 5 and with the expression x plus 1 over x. Okay, so to find the domain of any logarithmic functions, you take in what is next to log. So in our case, it's rational expression, and you solve inequality. This one has to be positive. Okay, so again, we have to review. This is rational inequality. So let's review how to solve it. So to solve rational inequality, okay, first make numerator equals 0. So we have x plus 1 equals 0, solve for x. So we're trying to get the x values which will divide the number line into intervals, and then we can test those intervals to see which one satisfy the inequality. So solve for x, we're getting x equal -1. Okay, so we have it, save that. Second, since you have rational inequality, you have to give the condition that denominator can't be equal 0. Okay, so your denominator is x can't be equal 0. Okay, save that. So when you solve those two easy equations, you're going to build to the test. You're going to build the number line. Okay, so that's our x values. And we make numerator equals 0, and we end up with x equal -1. Okay, you're going to keep your circle open because you have a strict inequality. And we know that x can be equal 0, so that always have open circle. Okay, so now like you see, those two numbers divide number line into 3 intervals. From -infinity to -1, from -1 to 0, and from 0 to +infinity. One or two of those intervals will be our domain. So we have to pick, we have to check. Next, we're going to do the test. So we're testing the interval from -infinity to -1. So here, you're going to pick a number which is less than -1. So I'm going to pick x equal -2. I take that -2 and I'm plugging in into our inequality. X plus 1 over x has to be positive. Let me just rewrite that. We're testing this one. X plus 1 over x has to be positive. So this is what we're checking. Okay. Okay, so when x is equal -2, we're having -2 plus 1 over -2, and we're checking if this is positive. We end up with -1 over -2, and that's definitely positive. So 1/2 is definitely greater than 0. Since this is true, the interval from -infinity to -1 is the domain. Okay, so I'm going to start writing down the answer. We got that, okay? That was true right here. So we already have domain. Domain will be from -infinity to -1. Okay, next what I'm going to do, I'm going to test the second interval from -1 to 0. So I'm going to pick here x equal -1/2. Okay, so now we have, let's plug it in. We have -1/2 plus 1 over -1/2. I'm checking if this is greater than 0. So we're getting 1/2 divided by -1/2. I'm checking if this is greater than 0. That will give me -1, and -1, it's not greater than 0, so this is false. Okay, since this is false, that's not my domain. And the last one, I should move that a little bit. Domain, and just erase that. Okay, so here, domain, originally we got from negative infinity to negative 1. And now here I'm going to test the last interval from 0 to infinity. So I'm going to pick any number from that interval. So I'm going to pick x equal 1. Let's plug in that 1 into the inequality. So we have 1 plus 1 over 1. I'm checking if this is positive. You're getting 2 over 1. That's definitely positive. So this is true. So the interval from 0 to infinity, it's going to be also our domain. So I have union of two intervals. Okay, so this is what you guys learn, actually how to solve those inequalities in section 5.4. Let me just pause for a second. So resume, we're going back. Okay, so this is how we finding the domain of logarithmic function. It's a long section, okay, so stay with me. Okay. I think it's a half. Next, what we're going to talk about, we're going to talk about natural logarithmic functions. Okay, natural logarithm functions. Logarithm function. So natural logarithm function is the logarithm function with base equal e. And again, don't forget that e is irrational. It's about 2.71. So any logarithmic function which has base e, okay, it's going to be written as ln of x. So we skip that base. Why? First of all, if you guys will look on this left side, if you're average person who, okay, if you never saw logs, okay, it looks very complicated even to read it. Okay, so what we're trying to do, you just need to remember that when you see ln of x, we call that natural logarithmic function. You guys need to know that each logarithmic function has a base. So here we have a base, and you have to remember that the base is equal e. We're just skipping writing that base, okay? Just for simplicity, we are skipping writing base e, but it's over there, okay? You guys need to remember. So ln of x is the same as logarithm of base e of x. This function, so y it's equal ln of x, don't forget that base it's equal e, and e is greater than 1, so this function is increasing. How you graph it? Okay, so to graph y it's equal ln of x, I'm going to graph with 3 major points. Okay, so 3 major points. You always graph with 1 comma 0, base comma 1, and 1 over base comma negative 1. So in our case, we're going to have e comma 1 and 1 over e comma 1, which is about e, it's about 2.711, and 1 over e, it's about, what is that, 1 over e? 0.37, I think. Let me just double check. 1 over e, 1 divided by e. E, again, depends on which calculator, about 0.37. 0.371. So E, again, make sure that you know how to find E on your calculator. In my calculator, it's next to division in blue, but you have to check, okay? You cannot just type 2.71. You should actually type E. So make sure that you know how to find E on your calculator. So natural logarithmic function, this is how the graph looks like. So we have 1, comma 0, 1, 2, 1, 2, 3, and so on. So we have 1, comma 0, first point, then e, comma 1, which will be 2.71, somewhere here, comma 1, and 1 over e, which is 0.37, negative 1. Sorry, negative 1. Right here. So this is y equal ln of x. Okay, still x equals 0, vertical asymptote. Okay, and another logarithmic function which you guys need to know, and because we're skipping base also in common logarithmic function. So next one, it's common logarithm function. So common logarithm function, this function has base equal 10, okay? We call common logarithmic function because we're using this base equal 10 a lot, and you write this as y equal log of x. So most of the books, when you have log and you don't see a base, so that means the base is equal 10. Okay, so you don't see the base here, but you need to remember that the base is 10. Okay, so y equal log base 10 of x. We're just writing as log of x. Okay, so don't forget, you don't see the base, it's common log, which means base is equal 10. Okay, so this function, okay, is also increasing. Okay, since base it's equal 10, you're going to graph this with 3 major points. Okay, so 3 major points, 1, comma 0, base, comma 1, so in our case it's going to be 10, comma 1, and 1 over base, comma negative 1, which in our case will be 1 over 10 and negative 1. So let's graph this function so you guys will see how they behave. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have a point 1, comma 0. Okay, 1, comma 0, x-intercept, 10, comma 1, right here, and 1 over 10, comma negative 1. Okay, so this one it's more flat comparing to ln. Okay, so if you guys will compare them, this is y equal log of x. So log of x, it's getting closer to the x-axis. Okay, it's more flat comparing to ln of x. Okay, next There are problems about graphing. I guess I'm going to do one example, how to graph logarithmic functions using transformation. If you guys will struggle with that, let me know. Since you're taking tests on the computer, you won't graph by hand, but you will have to be able still select the correct graph. So I only going to graph once, and I think that's enough. Okay, very long section. This section 5.4. Okay, so graphing. Next one, it's going to be example of graphing logarithmic functions. You know what, guys? I'm going to record that in next video because I still have the most important stuff, which is solving logarithmic equations. We still need to talk about graphing logarithmic functions using transformation, and I want to solve one more problem. So I'm going to stop here and I'm going to record video 3. Okay, so thank you for watching. Stop recording.